So good day class, today we'll be tackling the optical properties of our materials. So lecture 12, we have I think 3 lectures before we finish this subject. So the optical property of your material is the response of that material to electromagnetic radiation. Yung pinaka-common na form ng electromagnetic radiation na meron tayo, well, it's light. Oh yeah. So we can treat light as two things. First, we can treat light as a wave. So when we treat light as a wave, the energy of light, E, would be proportional to its frequency. Pag mas mataas yung frequency nung electromagnetic radiation natin, or what we commonly call as light, mas mataas yung energy niya. So it is proportional to constant H here. This is your Planck's constant. So the visible spectrum that we can see in our daily lives that is perceived by our eyes, ito ay maliit na part lang, sobrang liit na part lang nung ating full spectrum of electromagnetic radiation. So it's from 400 to 750 nanometers in wavelength. We can also treat light as a particle. In this case, we consider the particle called the photon. And this photon is basically one quantum of light, whatever that frequency of light is. So when we have light, when it strikes a solid, there are three different phenomena that can happen. First, it can be reflected by the solid, reflection. Other is pwede siyang i-absorb ng solid, or the other one is the light can pass through the solid. And in this case, your light would be, well, the energy is conserved. So basically, yung incident light mo, this will be equal to the intensity of the transmitted, the absorbed, and the reflected lights. To understand the optical properties of our materials, we have to understand what we call yung electron transitions natin. So when your electron is supplied with energy, so in this case, when we supply a photon to our electron, your electron can jump to a higher energy state. As so. See? Umakyat siya papunta dito. Since yung energy ng photons natin is discrete, this is dependent on the frequency of your light, your solid can only absorb specific photons. By this, we mean there are forbidden transitions na bawal mangyari sa ating solid. So in this case, let's say for this band gap, if your electron is here, bawal na hanggang dito lang yung transition mo. Since from your electronic or electric properties, wala kang allowable energy state dito, bawal pumunta si electron dyan since bawal nga. So electrons cannot stay in an excited state for a long time. After a while, after a very short while actually, your electrons will decay back to a lower energy state. And with this decay, it will release energy. So yung energy na pwede niyang i-release is either light, or yung tinatawag nating photon, or pwede ring phonons or heat. So for now, I think it is sufficient for us to know that your electron transitions can be a combination of photon and phonon decays. So like in this case, you have the release of 1 and 2 photons. Or in another case, pwede rin siyang phonon and photon. And meron din case na puro phonons lang yung release. So it depends on the band structure of your material, which we'll go into in a higher MatE subject, if meron pang MatE in the future. So since light is EM, electromagnetic radiation, it has both electric field and magnetic field components. And this would interact with your electron cloud. This interaction is what we call your electronic polarization. And your electronic polarization, what happens is we're inducing partial positive and partial negative charges. Pinapolarize natin yung ating atom. And in this case, pwede actually tayong magkaroon ng absorption of our light. In electronic polarization, we're actually decreasing the velocity of our light waves. And this is the reason kung bakit nagkakaroon tayo ng refraction in our, not just materials, but in our matter. So kaya pag tumingin kayo ng straw or ng something sa underwater, nag-iiba yung parang apparent size niya or distance niya dahil yan sa electronic polarization. So we have a property in our materials which we call the refractive index. The refractive index N, this quantifies the change in velocity of your material when coming from vacuum to a medium. N is always a value greater than 1, and N is equal to C over V, where C is the velocity in vacuum and V is the velocity of light in what matter we are dealing with, or in our material. The change in direction of light when going from one phase to another is described by Snell's law. In Snell's law natin, this is N1 sine theta 1 is equal to N2 sine theta 2, where N1 and N2 are the refractive indices of phase 1 and phase 2, and theta 1 and theta 2 are the angles with respect to the normal of the interface. So depending on the refractive indices of your materials, there are some cases in which light may pass through or sometimes hindi siya pwede mag-pass through to the next phase. Kakaroon tayo ng total internal reflection in our material. This happens when N2 is less than N1 or we're going to a less optically dense material. So the transition or the angle that we need for the attack of the from material 1 to material 2 can be given by this equation here. Theta C is equal to arc sine refractive index of the material we're entering over the refractive index of the original phase that we went from. In our materials, pag mas malaki yung size ng atoms or ions natin sa isang solid, the greater the electronic polarization in that atom or in that solid would be. This would mean that ang mangyayari is mas bababa yung velocity ng light natin, which would lead to an increase in the refractive index of your material. So we can see this in this kind of glass here. So itong glass na to, this is what we call lead glass. So in lead glass, the addition of lead oxide, lead is a big atom compared to the silica in glass. This actually increases the index of refraction from 1.5 to 2.1, which changes the optical properties of our glass. So now let's look at the optical properties of our different materials. First, let's look at conductors. Conductors, as we've described before, yung band structure niya is ganito. Wala tayong band gap dito. Since wala tayong band gap, yung next permissible energy level for our electron is very close to the original energy level. Very small energy is needed to cause the excitation of your electron from here up here. And since ganito nga yung band structure natin, through some other explanation na hindi nyo pa kailangan malaman, there's only a single decay path or isang decay phenomena lang ang kailangan ng electron mo para bumaba into its original energy level. So sa conductors mo, yung energy ng light na kaya nyong ma-absorb is from the lowest energy of light up to some value here. So now let's look at some examples. Yung conductors natin, usually yan yung mga metals. So let's look at metals. So let's look at some example metals. So first we have gold. So yung gold natin, ang kulay niyan is, well, gold. So sa bakal natin, ina-absorb niya lahat nung radiation, nung light natin. So from violet to red, kaya niya i-absorb. But since yung kulay nga nung gold natin is, well, gold, ibig sabihin, nag-release lang tayo ng yellow na light. So, in-absorb niya yung from red to violet. And sa decay niya, ang permissible na bumaba lang is yung yellow. So, in-release na is yellow. So for copper, yung copper, kulay ng copper mo is parang, well, copper. So it absorbs all light. So from violet to red, from Roy to Biv, kaya niya, kasama na yung green. But yung na-release niya lang is yung kulay niya, which is red to orange na light. So due to the band structure of our metals, they are very liable to absorbing all wavelengths in the visible light, which makes finding naturally transparent metals very unlikely. Though we can actually make metals transparent, but we need to make them extremely thin. So we usually have around less than 100 nanometers para magkaroon tayo ng degree of translucency or transparency in our metals. Now let's look at our insulators. Our insulators can have various optical properties. So nakita tayo ng insulator na transparent, pwede rin siyang translucent or opaque. But why is this so? So this, again, can be explained by their band structure. Tada! In your insulators, since now we have a band gap here, this will mean that very large energy is now needed to excite this electron up to the next permissible energy level. So looking back at the visible spectrum of light, we know that your visible light is from around 400 to 750 nanometers. If we convert that into energy, this would be from 1.8 electron volts to 3.1 electron volts. And this is important because this determines the property of your insulator, whether maging transparent siya or opaque. So the band gap energy then determines the optical properties of your insulators. If the band gap energy is large, your material would be transparent since it would not be able to absorb any light in the visible spectra. Magpa-pass through lang yung light mo sa material mo since wala ng permissible energy level to accommodate the rise of the electron when supplied with an energy from 1.8 to 3.1 electron volts. Then light will just happily pass through the material, leading to a transparent material. If your material has a band gap less than 3.1 electron volts, pwede tayo maging translucent. So, partial lang yung absorption ng light mo or pwede kang maging opaque. So, sa opaque, mangyayari is mababa na yung band gap mo, na-absorb na fully ng ating material yung all wavelengths of visible light. So these are just some examples of insulators. So diamond, transparent, 5.5 electron volts greater than 3.1. Alumina ranges from transparent to translucent depending on the impurities and how we manufacture it. And GAAS, this is opaque. Kita nyo, hindi nagpa-pass through yung light punta sa kabila. So now in our insulators, the color of these insulators can be dictated by how it absorbs light. So this explains why your emeralds are green, why topaz is violet, and why ruby is red. So for a translucent material, the color seen for that material is the complementary color of the wavelength absorbed by your material. So for example, if it absorbs green light, it would appear red. If it absorbs yellow light, it would appear purple. And so on. So let's take, for example, this. Cadmium sulfide has a band gap of 2.4 electron volts. If the band gap is 2.4 electron volts, we can see that the color that is absorbed would be from blue and higher. So blue to violet. And this would make cadmium sulfide appear yellow. Since yun yung complementary ni blue, ni violet, the blue-violet. Next, cinnabar appears red. Cinnabar appears red because it absorbs a complementary color to red, which is green. So by comparing the colors of our insulators, we can actually infer which between cadmium sulfide and cinnabar has a higher bandgap energy. So in this case, we can see that cadmium sulfide would have a higher bandgap energy since it absorbs a higher energy of light. So si cadmium sulfide kaya niya mag-absorb ng blue, which is more energetic than green light. So blue is more energetic than green light. So cadmium sulfide would have a higher bandgap energy. So in your materials, upon the addition of impurities into its structure, this would actually change the optical properties of your materials since we're introducing new energy levels into our material. So ito yung tinatawag nating impurity or trap levels natin. So these trap levels can change the optical properties of my material. Pwedeng mag-change yung refractive index, pwedeng mag-change yung kanyang translucency or transparency or yung kanyang color. So yung pinaka-madaling makita actually is yung color change natin. So this explains a lot of different phenomena on why our materials can change in color when we add certain impurities. So for example, you have diamond. Diamond is commonly white. The bandgap of it is really high. It's transparent. But when we add impurities into diamond, let's say boron or nitrogen, we're adding trap levels inside our diamond which can actually impose color into your material. So boron doped diamond is bluish, nitrogen doped is yellow. We also have corundum, and you have ruby is corundum with chromium impurities, and sapphire is corundum with titanium or iron impurities. We also have quartz. When we add iron into quartz, we get amethyst. So another factor that affects the optical properties of our materials is the presence of defects in your solid. So these defects may be pores or voids or grain boundaries, and these features might cause total internal reflection in our material, which would transition your material from transparent to opaque. So from left to right, we have your single crystal, polycrystalline, and porous materials. And nakita natin habang nag-increase or habang nagkakaroon siya ng defects, we're transitioning from transparent to opaque na alumina. So that is actually alumina. So the reason we study optical properties of our materials is not only to know kung ano yung magiging kulay niya or kung transparent or opaque ba siya, but your optical properties is also important in our optoelectronic devices. So one such is your LED. Yung LED natin, yan yung umiilaw pag pinas natin through a PN junction ang electricity. We also have solar cells, production of electricity from light, and we also have lasers. So the mechanisms of these devices, this will be discussed in another lecture in a future subject. But for now, kailangan nila malaman na these devices will tackle light. So with that, we are done with this lecture. So thank you and hope you are still keeping on keeping on. With that, I'll sign off and I'll see you next time. Thank you.